not just pretty lights, though, when it comes to the aurora borealis. In fact, some of these solar storms can actually disrupt and even damage technology on Earth. The Carrington event happened in the year 1859, stands as the strongest observed solar storm in modern human history. Now, that caused a lot of problems. It was back when we had the telegraph, but we almost had one in 2012. Earth narrowly missed that one. So if or when it happens, a solar storm that impacts the globe could become a $2 trillion disaster, because it is a magnetic energy that comes through with these storms, and that's where we could have problems. If it were to occur, might take a decade for us to recover. Some of the destruction of communication infrastructure could bring about the end of the internet. You heard me right. This idea was actually explored by a UC Irvine student. She researched the potential in her paper entitled Solar Superstorms, Planning for an Internet Apocalypse. One of the greatest dangers facing the internet with the potential for global impact is a powerful solar superstorm. Well, the federal government has actually assigned a team of scientists at George Mason University $13 million to study this potential internet apocalypse and keep us away or help us prepare for dealing with some sort of solar storm that could cause this. Let's bring in the principal investigator for the project. Professor Peter Becker is at George Mason University. Peter, solar storms causing the internet apocalypse. That sounds like a worst case scenario. What does it look like?
Yeah, well, as you pointed out, it's been in the news a lot lately. There have been articles all over the place, Wall Street Journal, Washington Post. But, yeah, the idea is there have been a lot of flares. Flares are when the sun brightens and we see the radiation. And that's kind of the muzzle flash. And then the cannon shot is the coronal mass ejection, as you mentioned. So we can see the flash, but then the coronal mass ejection can go off in some random direction in space. But we can tell when they're actually going to head towards Earth. And that gives us about 18 hours of warning, maybe 24 hours of warning before those particles actually get to Earth and start messing around with Earth's magnetic field. So, yeah, you mentioned the Carrington event in 1859. There was actually also a big flare in Halloween of 2003. And so the Carrington event actually was a coronal mass ejection that did reach Earth, and it totally wiped out the telegraph system. So the telegraph system was their internet of the day, and sparks were literally flying off the telegraph lines, and there's even rumors that some operators might have even been electrocuted. It was total mayhem, and the system went down for a matter of weeks. And, of course, a telegraph system infrastructure is very robust compared to the modern internet with all our little cables and fibers and things. So an event like that occurring now is something the internet is not built to handle. So we're talking not just the electrical grid, but huge economic consequences, especially because of the global wired economy now. So, yeah, if it happened now, if the Carrington event happened right now, we're talking $10 to $20 billion per day of damage to the U.S. economy alone, and possibly weeks to months to repair the infrastructure, because you're talking about all those little electronics closets and all the office buildings basically getting fried and hardware having to be replaced. Anyway, but the good news is we're monitoring the sun at Mason. That's one of the big things we're doing under this contract that you mentioned. And we actually have satellites watching the far side of the sun. So that gives you more advanced notice. We've got satellites called SOHO on the far side of the sun, and we're getting data from those. So that gives us a little more early warning. So the thing is, the sun's going to do what it's going to do. We can't control the sun. And in long term, we have to harden the infrastructure on Earth. But in the short term, at least if we have a warning, every minute counts, because you can put satellites in safe mode. You can take transformers offline from the grid so they don't fry. So there's things you can do to mitigate the problem. And then more long term, you're talking about hardening the internet. And that's, of course, an economic challenge, because it's sort of like an insurance policy. You may never need it, and it would cost trillions to really harden the system. So, the bottom line is always a driving factor. We don't really know if that's going to happen. So early warning right now is really the key for us.
So when you're talking about the magnetic energy, I kind of get that idea that coming into the Earth would be a problem, but killing the internet, how does that happen? Does it come in and just fry everything? Because then electrical grids probably would be very vulnerable as well.
Yeah, it's pretty insidious. You do get magnetic distortion of Earth's magnetic field, and that drives inductive currents that drive the power grid crazy. And the more you disconnect the grid, the safer it is. But the other thing that people don't realize is it can drive an inductive current through the surface of the Earth, too. And then you get this kind of insidious thing where you can actually get current from ground. So everybody thinks, oh, if my computer's grounded, I'm okay. But in an event like this, if you drive inductive currents to the surface of the Earth, it can almost work backwards, and you can end up actually frying things that you thought were relatively safe. And another side note, sometimes people think, well, we're okay because we have fiber optics. Not really, because fiber optics, it's true that the light isn't affected, but the problem is that you still have sheaths of copper involved in all this stuff. And even undersea cables, which are fiber optic, still have copper sheaths, and they also have repeater transmitters periodically on the ocean floor, and those run on electric power. So even the undersea cables could possibly be fried. And by the way, some of these events, so we mentioned that the Carrington event of 1859, there's evidence for much larger superstorms in the past. They found evidence for enhanced carbon-14 in tree rings in France and also in ice samples in Greenland that show that there were huge flares, maybe hundreds of times stronger than the Carrington flare. And what happens is the solar radiation actually enhances the production of radioactive carbon in the atmosphere, and that filters down and gets taken in by living things. And we can see 14,000 years ago in the tree rings, there's a big spike in this carbon-14, indicating a huge amount of solar particles were stimulating the production of this radioactive carbon-14 at the time. Now, in an event like that happened, again, totally unpredictable, but you can't predict solar flares any more than you can predict earthquakes. But a super flare like that, then you're talking pretty much off the books. We don't really know what something like that would actually do. We haven't observed that
I'm interested
in recent human history. I mean, 14,000 years ago.
Peter, before you go, we only have a few seconds left, but how would we find out? Is there a warning system that'll be in place in case you capture that we only have 24 hours to prepare? How will we know about this?
Yeah, I think it probably wouldn't. I mean, I don't think ARID sirens would go off or anything like that, but the word would spread through power grid operators, satellite operators, DoD. You know, DoD systems are more robust than commercial systems, but still they have to take those offline. So basically, there would be, we would know about it publicly that there's a big flare coming. And I suppose, people would be warned and probably would disconnect stuff, actually, if it was a large enough event. But yeah, the power grid operators would know. And again, we can probably mitigate the problems with the early warning. So that's really the key. So that's one of the main things we're doing at Mason is watching the sun, but also modeling the sun to try to improve our predictive capability and understand better the connection between the flare, which remember is the flash. The flash reaches us in 8 minutes, and then that's when the clock starts ticking, and we have 18 to 24 hours. So the more time we have
hate to interrupt you because it's so